Thank you, Astroboz. So here we go. Gravitational waves, gold, bling, and the Twitterverse. I'll work all this in as we going here. I want to first start talking about gravitational waves because that's the critical idea going on here. As I talk to you, I make sound waves, but there's no molecule goes from my larynx to your ears. I'm sending out pressure waves that compress air and it expands and compresses and expands. So that signal of the compression goes from me to you, registers in your ears. That's the way a sound wave propagates. An ocean wave, you know, ocean waves bob up and down. You might kind of picture a water molecule bobbing up and down. But of course, no water molecule starts on one side of the lake and goes to the other side. It's that the molecules bog up and down where they are. They actually sort of go backwards into a trough and spiral around and back to where they started from again. Well, gravitational wave is like that. It's a wave. It's an influence that propagates through space. It is actually a curvature of space itself. Einstein's amazing insight about 100 years ago. And then it makes a particular reaction to things when it gets there, and this little movie captures that at some level. If we had a gravitational wave coming down and impinging on the screen and a bunch of dots just floating in space in a circle, that's how they would respond. It sort of compresses sideways and then outward and sideways and outward like this. And to sort of pick up on this, make it a little bit more visceral and relate to how this is actually done, I want to get a little audience participation here. So let me try the following thing. I'm going to pick on the second row just because the first row is a little thin here. So if I could get you folks from you on over to watch that dot over there, hold your hands up. And then just follow that dot. So when that dot on the right goes over, then back, over and back. Okay, so starting here, then if you folks could hold your hands up and follow the dot on the left. And so when it goes, you go that way. And then you folks along the aisle here, if everybody just along this aisle could hold your hands up, you're off the aisle. You're going to confuse them. It'll get more confusing. I want you to follow that top dot. Okay, so there we go. So this one's going this way when these people come this way, and then this one's going this way when that one goes that way. They're out of phase exactly that way. So if we had a gravitational wave coming down from on high and landing in this room, this is the pattern of response we would see. This way and that way, and this way and that way, out of phase with each other, exactly out of phase. These come in when that goes up, these go out when that one comes down. So that would be the pattern. Thank you, folks. That was brilliant. Okay, that's the way gravitational waves work. The point being, if you have two astronomical objects in orbit, and it helps if they're particularly compact and massive. So things like black holes or neutron stars do this effectively well, and that's what we've detected in the last couple of years, and basic theme of what we're going to talk about tonight. So if you have two black objects of any kind, it could be two planets for that matter, or white dwarfs is another topic. Barbara's going to talk about white dwarfs, I think, later. So as these things go around each other, they make waves that go out through space. They're actually waves in the curvature of space. But what the peaks and the troughs are represent either squeezing this way or squeezing that way, the way you just illustrated. So this little movie, which is showing as things go around, it's a cartoon animation that you send off this curvature of space to make the gravitational waves. Point being, if you actually have, not illustrated in this movie, I have others, but this one I didn't pick that up because I can do it in the following way, I think. Let me go back to the, sorry. I've got a couple of neutron stars here, and the point about they're radiating from their little magnetic poles, bless their hearts. And the point is, if you have two things in orbit, as you're sending these waves out, as illustrated in this illustration here, you're taking energy out of the system. So you're sapping energy from the velocity of the rotation of these objects. They can't maintain their orbit because you're taking energy out of it. They fall inward, but as they fall inward, they're closer to each other, there's higher gravity, and they go faster. So they generate even more gravitational waves. So they fall in even more generate more gravitational waves. So in fact, they don't just go in orbit, they have to slowly come together and then eventually merge. And so here I've got two neutron stars, and as they spin around, they go faster and faster and faster until they will finally merge. And bam. Okay. So it's faster and faster and faster. Got this from the AAS meeting for your astronomers just a week ago. So that's what we're looking for, a particular pattern of gravitational waves that have a higher and higher frequency as they spiral together. So which machine I'm pushing here. So that brings us to the detectors. This is an amazing story. We've had an Astronomy on Tap talk on this a year and a half ago, maybe. So I can't reproduce all of that, but these are the two stations of the detector. Short is LIGO. It stands for the Laser Interferometer Gravity Wave Observatory. There's one outside Baton Rouge, and there's one in Washington. And they have a configuration of a miles-long pipe, one going this way and one going that way. Here, this one goes that way, this one goes that way. And that represents basically what I did with this row of people. Though part of the wave has you going this way, and at the same time, orthogonal to that, you've got it going that way. So you've got this pattern of in and out and in. I tried, there we go, like that. But perpendicular to each other. So as this one gets shorter, that one gets longer. It gets stretched by this gravity. And as this one gets shorter, that one gets longer. In exactly the way I tried to illustrate there with the audience. And that's why it is this perpendicular L-shaped structure. They're looking for exactly that pattern. And they want to see whether it happens in this one and so a couple thousand miles away. At the same time, they know they're seeing something real, not just vibrations. I've got a yo-yo demonstration here about how you stabilize these that I'm going to skip for right now. The guy who gave this talk showed how that works. I'll skip it. Anyway, so this is the detectors. And this was a 30-year struggle of trying to build this thing. It's an amazingly sensitive device. So you could think of this thing's getting longer and shorter and that thing getting longer and shorter. But they can measure how much that length changes by a fraction of the wavelength of the laser light, which is already small, and they can measure a fraction of the change of the wavelength. They can measure how long that pipe gets shorter by a distance smaller than the size of a proton. It is perhaps the most sophisticated physical engineering thing ever done. Under design and construction for 30 years until they finally turned it on in 2015. And during the first engineering run, wham, they saw the signal. And out of that signal and others that followed, that was the Nobel Prize this last year. So that's a whole story. I'm not going to tell that one in detail because I want to get to the neutron star version, which is a more recent thing that I've been somewhat involved in myself. But so since they turned this thing on in 2015, they saw gravitational waves from two black holes spiraling together in a very characteristic way. And it turned out to be two 30 solar mass black holes. And we've seen black holes out there in the universe before. I work on kind of solar mass ones. Carl works on supermassive ones. But we didn't know that ones of that rather massive size for a star type black hole existed. And this first event told us it did. Counting that one, there's been 3 more. There's now 4 total black hole events since they turned it on in September 2015. Just an absolutely incredible piece of technology and a lot of understanding how to use Einstein's equations on a supercomputer that also was a 30-year process going on. So this was the result from the very first detection, the famous chirp heard around the world. How many of you knew about that chirp when it happened at the time? In this audience, I think quite a few. So what happens is you get a pattern of these things spiraling together and making waves going faster and faster and faster and a higher and higher amplitude until these two black holes merge into a single black hole. And so the chirp consists of that signal getting higher and higher amplitude and closer and closer together, both in Baton Rouge and in Washington. And the subsequent thing, if you turn the gravitational wave frequency into a sound, this is what it sounded like. It's a chirp that goes whoop, as these two things finally spiral together and merge. So that's what the chirp was. The whole thing lasted only about a second, fraction of a second for these two black holes. Been millions of years coming together, but the final thing was just this fraction of a second when it was detected. So that's what the Nobel Prize was given for. So what I want to skip to, because that's a huge story, but I'm going to skip to this chapter of it, is this is an object called GW for gravitational waves, 17 for 2017. It was discovered in 2017 in August 08 and the 17th day. So August 17th. So this turned out to be the same kind of thing, but the chirp was 100 seconds long. So it was a much longer thing for these two things to come together. And in fact, that was a hint that they are smaller mass objects. It take a little bit longer to do that. And already just from that information alone, people suspected it was two neutron stars spiraling together. It turns out that that original gravitational wave chirp was followed by 1.7 seconds later by a flare of gamma rays. And so that set off a whole adventure that I'll talk about here a little bit. And basically this was the advent of what people are calling the multi-messenger gravity wave astronomy. Point being that gravitational waves are not like electromagnetic radiation. They're not like light. They're not like photons. The standard grist for astronomers. It's a completely different physical phenomenon. And so we have an electromagnetic signal as a messenger that this happened, and the gravity wave signal that this messenger that this happened. So multi-messenger astronomy is the buzzword of the day. The other important thing to note is that when two black holes spiral together, black holes are just entities of space-time. There's no matter there. They're just curved space. And they merge together and they make another bigger black hole out of curved space. They do not make any electromagnetic radiation at all. It's just two space-time things coming together making a bigger space-time thing. Neutron stars are exotic stuff, very highly dense neutron matter, but it's real stuff. And when you bang them together, it makes electromagnetic radiation, and now ordinary astronomers can get in the game and follow up on it. And they did in spades. There were like 4,000 astronomers around the planet that got on this and wrote like 1,000 papers in a short amount of time. So here's a cartoon illustration of the two neutron stars coming together. I don't know that they're white. Mine were black. I don't know what these guys are doing. Swirl of stuff around it, the gamma ray magnetic jet coming out of it, wrinkles of space-time going off, excuse me, being captured in this cartoon version of it. So here's what happened with the electromagnetic radiation. So there were satellites that saw the gamma ray burst, but the real excitement in the astronomical community is you could look at this with ordinary telescopes and see what was going on. Again, because there's electromagnetic radiation, not just gravitational radiation. So when this thing was detected, it was in the daytime. The astronomers had to wait for the sun to set, sitting around twiddling their fingers until they could do something with their telescopes. But as soon as they could, basically as soon as the sun set, there were groups all over the world that had different techniques for saying, okay, I know roughly where this thing is. Let me go see if I can find an optical transient to go with it, because the suspicion it was a neutron star was there. And so when the Fermi satellite first saw the gamma ray burst, it said, well, here's a patch of sky. This is actually in the southern hemisphere. South is up that way. A big patch of sky, not well focused, just over there in that part of the sky. Then the gravitational wave detectors came along and triangulated on it and said, well, actually, it's a smaller patch of sky. You all ought to be looking here. And so here's a blow up of that. There was a group, I think, at Carnegie Observatory that got a telescope at Saratoga Observatory first on it, 11 and a half hours after the original burst when the sun finally set. But then within 15 or 20 minutes, there was another group and another group and another group. They all had different techniques, but they all ended up isolating this thing and seeing that spot of light. So our friends here at Las Cumbres Observatory, they have a station out at McDonald Observatory. One of the key people there is Andy Howells, an ex-student of mine who gave a wonderful Astronomy on Tap talk here about a year ago. But they looked, and they looked in this patch of sky at a bunch of galaxies, and they found this one had a new light in it, and it turned out to be this new object. This has been labeled a kilonova. There were theoretical calculations, computer simulations of what happens when two neutron stars collide together. So this was a game that you had to confirm with observations, but the theorists were all over it, understood basically what's going to happen when this happened. And the prediction was that the light from this thing should be dimmer than a supernova, but brighter than an ordinary nova by about a factor of 1,000, which is where that kilonova comes in. So that's become a popular phrase for the optical light that goes along with two neutron stars colliding. So let me tell you a little bit about my adventures in the Twitterverse. I was at a meeting in Pasadena on that week of August and sat down at breakfast, and one of my colleagues came down and sat down, and she was just all energized, and she said, something really exciting has happened. And I thought, well, she's at an institution that's connected with LIGO. It may very well be something about gravitational waves. And by this time, we'd had 3 black hole mergers reported. So I registered that, but they're under embargo not to talk about it. So she didn't say what it was. She just said something exciting. And okay. So we had our meeting, went on. I came back to town. On that Friday, the 17th, I was off to see the eclipse. Tried to meet up with some family in Kansas City, which turned out not to be the best place to go. But I was in transit in Dallas, and I got a call from another colleague, and we talked about another scientific thing. And at the end of the conversation, he said, there's been a neutron star collision with an optical transient associated with it. And I thought, oh my God, this is really cool. And I already had a hint because of this breakfast thing earlier in the week. So, oh man. And so I thought, I've heard about this twice now, and so surely this is going to go public within hours. And so I said, okay. I got out my phone and I tweeted. And I said, I should have put the actual tweet up here, but I'll paraphrase it. Something like, gravitational wave neutron star mergers with an optical transient. It'll knock your socks off. That was literally what I said. And then I flew off to watch the eclipse. And over those few days, I thought about it, and I realized that was really an unfortunate thing for me to do, because the first person didn't tell me what was going on, but if I talk about it, somebody might put that together. She was under embargo, and I didn't want to violate that. The second colleague was definitely under embargo. He should not have told me that. And so I should not have put either one of them in peril. But so what I ended up doing about 3 days later was send out another tweet apologizing for having done it, saying LIGO gets to sit on this data as long as they want to make sure it's analyzed properly. They've got all the signal and all the noise understood, and announce it when they want to. And that was basically that, except that this tweet had gone out and it ricocheted around the world. And so all sorts of people thought that I had some magic insight into what was going on with this thing. And so my Twitter account just started exploding over the next little bit. I had something like 50 followers at the time. I downloaded this last time, 849, and I've got a few more by now as well. One of the recent ones was this McConaughey person, but if you look closely at the picture, it's not the Matthew you're thinking about. It's another McConaughey. Anyway, that was a real trip. Then it turns out I got invited by the Astrophysical Journal letters to referee some of the papers that were being written. Harvard University alone published 8 papers on this object, of which I refereed 2, and I refereed another one for another group. And as I was doing that, I'm looking at this, and they're saying this thing went off on the 17th. And I go, wait a minute, this colleague of mine in the breakfast meeting, that was 4 days earlier. And so I had to talk to the editor. I want to make sure I'm not confused about this. And he emailed back and he said, nature can be very rich in its bounty. And it turns out there were 2 gravitational waves in the same week. The Monday one that my colleague talked about was a black hole merger. On Friday was the neutron star merger. So I finally got that all sorted out. But 849 and counting. I have no special insight at this point. Okay, well, what about bling? So one of the basic points, there's a lot to talk about the astrophysics. Because of the short talk, I want to try to get to this. We've been trying to figure out where heavy elements come from for a very long time. Question of where they come from normal massive stars that Iron cores collapse and make neutron stars, and when they explode, they may make the especially heavy elements. But people have, in the past few years, theorists doing these simulations said it could very well come from binary neutron stars. And when people looked at this, they already had suspicion that you might make heavy elements. They would change the way radiation comes out of it. They found clues for that. There is evidence that indeed this massive neutron star merger produced heavy elements. What heavy elements? Well, it turns out a lot of them are in this row down here, the so-called lanthanides. Here's lanthanum itself, weight 57, but it makes a whole bunch of things. But it makes things back in this line as well, and famous in that line is that one, which is gold. So there is now a plausible argument that essentially all of the gold in the universe, including the bling you're wearing tonight, I'd say a few fancy bangles, but more wedding rings than not, come out of these colliding neutron stars. I'm not completely convinced they're all of it. I think it may be a combination of two things, but the smart money is basically arguing that all the gold in the universe came out of these exotic neutron star mergers. So there's a lingering question then after this rush. This thing, I didn't say this explicitly, this thing came and went in about 3 days at the time that optical astronomers could see it. Got up to 1,000 times as bright as a classical nova and is gone. But it left behind this question, these two neutron stars, and we know they're neutron stars because of the slow merger and other evidence, came together. Did they make one big neutron star, or did they in fact go over the limit and make a brand new black hole? And that question was left open at the time. And a few of us here talked about that and realized we could do something about that. There's a cartoon neutron star with its magnetic fields coming out, making little red lights like I showed you earlier, and a black hole. So those are the two possibilities. There's a couple of things about those suggestions. A so-called debris disk, just leftover crap around the black hole that formed spirals around it, could make X-rays. And if there's a highly magnetic neutron star, and we think any merged neutron star would have a strong magnetic field, it would make even brighter, more intense X-rays. So both of them suggest you should see X-rays. So we call on the Chandra X-ray Observatory as a tool to try to check on whether we've made a black hole or left behind a large neutron star. So we teamed up with Dave Pooley, my colleague who works at Trinity University, is in one of the premier users of the Chandra Observatory, and Pawan Kumar, my theoretical colleague at UT, who's thought very deeply about these things, how you would make the X-rays and what you would expect to see. And we submitted what is called a director's discretionary request. Any observatory, including McDonald Observatory, keep some time behind. If something really exciting happens, they'll let you use that for that. So we put in a request to interrupt the schedule of the Chandra Observatory and make X-ray observations with the Chandra Observatory. A couple of other teams did as well. I'll come back to that. And then Dave said, we put in the request in the 1st of November, but the observations weren't to be made until December. We had a month. Dave said, we should write the paper now. Write the paper, leave the answer blank, and then when the data comes in, we'll fill in the blanks and submit it, and we'll beat those other teams to the action. So that was the plan. We sat down and wrote the paper, and how X-rays would be made, and if it's this, well, it'll be a neutron star. If it's that, it'll be a black hole. So we had the paper all written, and the observations were made on December 7th. And here is the evidence for what happened. This was back in August when the thing first went off. Some X-rays were made at the time. A few days later, September, some X-rays were made. Here we are with a new observation and clearly more X-rays. Okay, now that really goes knocking your socks off. We were very excited about that. We think that can't be a black hole. It looks like too bright to be a black hole. So maybe we have found that a very massive magnetic neutron star survived. And that was basically what the paper was prepared to predict, and then either write in black hole or neutron star. So that's what happened, and in the observations came, and the answer was neither. It turned out there was, if you look carefully quantitatively at the X-rays and how they changed from September to December, and there were some radio observations that constrained things, that original jet that came plowing out, made the gamma rays, is still plowing out through space and heating interstellar gas and making X-rays in a somewhat surprising way. Thought it would fade, in fact is getting brighter, but all the physical data suggested we were seeing the jet and neither a neutron star nor a black hole. So we got those observations. This was on the afternoon of December 7th. Paul stayed up all night rewriting the paper, taking into account other observations and whatnot. It turned out it wasn't even the new observations. Looking back at the September observations already, once we thought about it, ruled out a highly magnetic neutron star. It would have already been too bright for what we saw in that September. So the merger most likely left behind a black hole. That's what we're going to claim right now. So we're planning more X-ray observations. In fact, we've asked for another series of them. Chandler X-ray Observatory is going to be making those observations just about now in the next couple of days. And then we'll ask for more and try to get a pattern. Eventually the jet luminosity ought to turn over and we might finally see a black hole debris disk or a neutron star. So we expect to see a black hole at this point. And then even more exciting, so I'm saying stay tuned here for the X-ray observations, but the fact that LIGO turned on 2 years ago, it has found 4 black holes and 1 neutron star already, means this thing is going to be really productive. We have really opened up a brand new window of astrophysics to look at the universe in a completely different way, and this story is just going to go like blazes from now on. Thank you very much.
Thank you, Professor Quantum. So, we have some time for questions. First, from the Twitterverse, actually. Jess Barton 13 has asked, so you mentioned 2 LIGO observatories. Are those the only ones that exist?
No, they're not. There's another one in Italy called Virgo. It is not quite as sensitive. For this particular thing I was talking about, the kilonova, it was sensitive enough to say it can't be in that part of space or that part of space. It's got to be in this triangulated space, but it didn't help to say what the actual amplitude was. But it was incredibly important for identifying where, and from where you could go to find the actual optical object. So, and there's going to be one in India and maybe one other. So this is, once people showed that it worked, there's going to be all sorts of effort to reproduce it and build more of these things.
So, question right there.
Yeah, so hypothetical. Suppose one of the neutron star, I don't know if it's possible with binaries, but had already been a millisecond pulsar that we could detect. What do you think would happen to the signal of the pulsar when the merger happened?
Well, so the question is, if one of the pulsars were already a millisecond pulsar, so rotating very rapidly and magnetic, it turns out millisecond pulsars have relatively weak magnetic fields. But I think, and what we're saying in this paper, what we're looking for, is in that merger, you stir these two things together, and they're swirling around very rapidly, and that condition automatically takes any existing magnetic field and amplifies it greatly. And that's what's going to make the X-ray signal. So my answer would be a really interesting way to pose the question, that the initial conditions, as long as you have some magnetic field to seed the process, the initial conditions are irrelevant. You're rapidly going to generate your own magnetic field out of the rotational energy of the neutron star. There was one over here, and then I'll come back to you again. Yeah, sir, please.
So waves tend to get smaller the farther they are away from the source.
Yeah, they're weaker. The farther, it's a 1 over distance squared kind of argument. Yeah.
What kind of distortion, spatial distortion, closer to the source?
I'm sorry, a little louder in the ladder.
What kind of spatial distortion would there be closer to the source of those converging neutrons?
I'm not quite getting the thrust of the question.
If we can detect like very minute changes in distance,
Yeah.
how great?
Oh, how far away could they be?
No, it's like if you were closer to the actual merging.
Oh yeah, you'd die. I didn't emphasize this, but the power of those gravitational waves coming out is huge. And so there's so-called tidal forces that if you were really close nearby, you'd be very uncomfortable. So it's a very powerful thing nearby, and then it gets weaker and weaker and weaker by the time it gets to Louisiana. So the kilonova was 40 million light years away. The black hole sources have been of order 1 billion light years away. We're looking at a long way. Okay, now please over here.
So we had an optical event 1.7 seconds after the kilonova came together.
X-ray strictly, or gamma ray strictly speaking. But yes, go ahead.
So this brings the question: do gravitational waves, are they faster or slower than light waves?
Yeah.
And why?
No, we know exactly the answer to that thanks to Professor Einstein. They go at exactly the speed of light.
Is there a reason why?
Undoubtedly. Can I come up with one in a short amount of time? You know, they're probing, gravitational waves are probing space and time in a very fundamental way, and that's what the speed of light is. It's sort of how fast ultimate things with no mass. How the gravitational wave has no mass, photons have no mass. And some of that is the reason why they go at the same speed. Neither one of them has any mass. Yes, ma'am, please.
Last question.
But are they in any way affected by potential time dilation?
By time dilation? Yeah, I mean, so things that are further away, we see the time flowing more slowly. So we see the light from this thing going up and down in 3 days. We know it actually was faster than that, you know, in the host, and it looks slower than that to us by a factor of 50%.
The sound that we get on light?
I'm sorry?
Could it affect the sound that's searching here?
Yes, and I think that's taken into account when they do that. It turns out that's a simple effect. You know how far away it is, you know how much the frequency gets stretched out, you can decompress for that. So I suspect that was taken into account. So that little movie with the chirp was meant to be, no, I'm sorry, so that movie was what did the detector see? But if you want to understand what happened at the source, then you take that into account to say, okay, this is the mass of the neutron stars and how much energy they gave off and how much mass they gave off. You take that time shift into account, for sure.
Okay, great. So let's thank Professor Quantum again.
Thank
He'll
you all
hopefully
very
be
much.
around during intermission if you have more questions.